Okay, here we're going to look at orbits. And for orbits, the way we're going to deal with them is we're going to have a large central mass. So we'll take its mass to be very much larger than the mass of another object orbiting it. Other object could be a moon, could be an artificial satellite. And we're going to say that the radius of the central orbit is capital R. The smaller mass will orbit around at a height h above the surface. And what we want to do is find out how fast is the satellite going and what is its orbital period. We'll analyze this motion by using F equals ma. We'll draw our free body diagram, apply F equals ma, and then calculate the velocity and the period. So to set this up, our free body diagram would simply show the only force acting on the satellite will be the gravitational force directed towards the center of the larger mass. Its force would be simply g times the central mass times the satellite's mass divided by the radius of the orbit squared. Remembering the radius of the orbit would be this height plus the radius of the central mass. The object will be going around in a circle, so that means it'll experience a centripetal acceleration of v squared over r. We then set this is the only force, so that is the F. Then we take the mass of the satellite times its acceleration, and here we have F equals ma. Notice that the mass of the satellite cancels out, and one of the r's cancels out, and from that we can calculate the velocity of the satellite. The period will simply be the circumference, 2 pi r, of the orbit, divided by its constant speed, v. So we can then take an example, let m be the mass of the Earth, and here's the mass of the Earth. Here's the radius of the Earth, remember it's in kilometers, and altitude above the surface will be 200 kilometers. Again, kilometers, remember to convert those to meters. So take a moment, I'm going to pause the video, and calculate the orbital speed and the orbital period. Okay, the answer would be the speed is right here. It's about 7,000 meters per second. They are moving incredibly fast. The period in seconds is 5,300. That doesn't really have terribly much meaning, so it's probably better to convert that into minutes. And that means the orbital period is something like an hour and a half. So the satellite in an orbit of about 200 kilometers, and that's not unusual. That's what's called a low Earth orbit. The satellite completes one revolution around the Earth in about an hour and a half. Okay, we'll look at another example. Instead of orbiting the Earth, we're going to be orbiting Mars, and we could say that NASA wants to put a satellite in orbit around Mars at an altitude of about 450 kilometers above the surface. We can use the same sort of analysis to find the orbital velocity and the period of this satellite. Here's the mass of Mars, and here's its radius. So take a moment and calculate the orbital velocity of this satellite and its orbital period. Okay, the solution is, again, the analysis is exactly the same. The only difference is the numbers you're putting in. The velocity turns out to be a little bit smaller. It's in a weaker gravitational field. And the period is longer. Remember, r is the radius of the planet plus the altitude of the orbit. And notice, again, the mass of the satellite is irrelevant. It cancels out of everything. All objects fall at the same rate. Another thing we can use this sort of analysis for is rather than calculating the orbit of an object, we could measure the orbit of the object and therefore infer what is the mass of the central object. And this is how we get the masses of planets. So let's take Saturn as an example. It has a satellite called Titan. It's one of its moons. Its period is just about 16 days, and here's its orbital radius. Now, in this case, the radius is in fact measured from the center of the planet. And in this case, the size of the planet tends to be relatively small compared to the radius of these moons, or other orbits of the moons. The eccentricity, I list here only to show that this is in fact in a very close to being circular orbit. If you were to draw an ellipse with this eccentricity of only 0.0292, you would find that looks awfully much like a circle. So this is pretty close to being a circular orbit. So take a moment and use the same sort of analysis and calculate the mass of Saturn. Okay, when you do that, we take the same equation we used before, only now we solve it for m rather than v. And v we can calculate because we know the radius of the orbit. Its period is in days. We convert that to seconds. Remember, the radius was in meter and kilometers. You have to convert that to meters. You calculate its speed. You can plug that in here. And you get its mass being something like 5.69 times 10 to the 26th kilograms. The accepted value I just pulled off from NASA's website is 568.34 times 10 to the 24th kilograms. These two numbers are very close to being the same. Remember, this is 500, so that's 5.6834 times 10 to the 26th kilograms. Two numbers are very close to being in agreement. Now, those are all for circular orbits. What if, in fact, the orbit is elliptical? Because in general, they are ellipses. They're not perfect circles. So first, just to get some vocabulary, how do we describe an ellipse and then an elliptical orbit? So first, to describe an ellipse, we usually cite what is known as the semi-major axis. This right here is the major axis. It's the longer of the two. Half of that is the length of the semi-major axis. That's generally called A. The other axis is called the minor axis, so we can take the length of one of these sides and again call that the semi-minor axis. The ellipse is defined as the distance between one focus and the planet and the other focus and the planet. As the planet goes around, the sum of those two distances is a constant. So for example, one way to draw an ellipse is you put a pin right here, put a pin right there, and take a string and wrap a string around here and simply circle around here and you will make an ellipse. So here's one focus, here's the other focus. The central object is at one of them, one of the foci. If it's an ellipse, that means the two foci are not at the center of the ellipse, they're off center, hence this is called the eccentricity. And the eccentricity is equal to the ratio of the distance from the center of the ellipse to the semi-major axis. So C over A is the eccentricity, or C equals E times A, with E being the eccentricity. So those are the basic terms we use to describe just an ellipse. Now, if the ellipse is actually an elliptical orbit, we call the closest point the perihelion, if the object is orbiting around the sun, the perigee, if it's orbiting around the Earth, or the periapsis, if it's just in general orbiting around an object. The farthest point is the aphelion, if it's the sun, the apogee, if it's the Earth, and the apoapsis in general. So that's the farthest point is the one with the A, the closest point is the one with the P. Now, just one other point here is the semi-major axis is actually the sum of the apogee plus the perigee divided by 2, because the major axis, I lost my place. The major axis is the distance from the apogee to the perigee, so the semi-major axis is half of that. Now, how do we apply some mathematics to describe this orbit? Well, we can apply two different conservation laws. This would be a closed and isolated system, and the force involved would be gravity, which is a conservative force. So we can use the conservation of energy, the sum of the kinetic and the potential energy, 1/2 mv squared minus gmm over r, will be a constant. So the object will have a constant total energy as it orbits around. In addition, since the only force acting on the planet is gravity, gravity is a centrally directed force, and therefore it applies no torque because gravity points inward. R is from the center of the star or the planet out to the satellite, and there's no angle between the two, so therefore gravity exerts no torque. Angular momentum will be constant, so R cross P will be a constant. Now, we can't use the conservation of linear momentum for a single planet because the gravity does exert a force. It is constantly changing the direction as well as the speed of the object as it goes around. So linear momentum is not conserved. However, if we take the system as a whole, both the satellite and the central mass, there the momentum would be conserved. So as the planet is going this way, the central object would be going that way. When the planet is going up, the central object will be going down, which means this object will be, even if it is very massive, will be wobbling around a little bit. And it is that wobble that is sometimes used when you look at distant stars to figure out whether or not there is in fact a planet orbiting it. Now, first I want to consider some qualitative questions. And we'll take a satellite that is initially in a circular orbit around, let's say, the Earth. And at this point right here, we'll have that satellite undergo a small change in its velocity. We want to see what's going to happen to the orbit. First, if it loses a little bit of velocity, and second, what happens if it gains a little bit of velocity. So you should take a moment, maybe you want to pause the video again, to see if you can figure out what would happen if it first gains and then loses a little bit of velocity. Well, if it's going to lose a little bit of velocity, that means normally it would have enough energy to reach this point on the opposite side. It has less energy now, so it won't be able to rise up to quite this altitude right here. So instead, it will only reach this point right here. Namely, it will be in an elliptical orbit where the Earth would still be at the foci of the orbit, only now the ellipse that it'll be in will be completely inside the circle because it has less energy. Conversely, if it gains some velocity, now it's going to be going to rise up above this old circular orbit. So instead, it'll reach a higher point, which might be this point out here. So again, it'll be in an elliptical orbit. The Earth would still be at one of the foci, but now the ellipse would be outside of the circle. So if we want to basically, we're in a particular orbit and we want to change it, we change a little bit of velocity by burning some fuel, for an example. We can basically either increase or decrease the speed of the satellite and move it to a higher orbit or a lower orbit. Now, one example of an elliptical orbit is what's called the Molniya orbit. That was used by the old Soviet Union for communications satellites, and they were highly elliptical orbit. The apogee was at a much, much greater altitude than the perigee was. And what we could then use is the conservation of energy and the conservation of angular momentum to find out how fast was the satellite going up here at the apogee and how fast was it going down here at the perigee. So we can find these two velocities. So we can say we have the conservation of angular momentum, which means the angular momentum at the apogee and the perigee must be equal. Notice the mass of the satellite will cancel out again, so we'll have the two velocities in the radii right here. Remember, the radius includes the radius of the Earth plus its altitude. We can also use the conservation of energy at the 2 points, 1/2 mv squared minus gmm over r squared, not r cubed. That's a typo. I'll fix that. That's a typo. So here we have conservation of energy. Here we have conservation of momentum. Take those two. It's two equations and two unknowns. It's a little bit of nasty algebra to do, but then we can solve for the two velocities. And the velocity at the perigee down here will be very fast. It's almost 10,000 meters per second. The velocity at the apogee is much, much slower. It's only 1,500 meters per second. And the reason this was useful for a communication satellite is right here, notice it has a wide field of view. It can almost see most of the Earth. And it's going fairly slow, so it'll stay in this orbit for a fairly long period of time. So it could therefore be used for telecommunications over a wide area for a reasonably long period of time. And this is a easier orbit to put in rather than a geosynchronous orbit, which it needs more energy to stay up at that altitude. And here it doesn't have quite that much energy. Okay, and I will fix that on the output. Now, the last example I want to look at are binary stars. So here we have two stars that are orbiting around their common center of mass. The example I want to consider is a simpler example than this one I have diagrammed right here. We'll have two identical stars orbiting around their common center of mass, so they have the same mass. But the way you know that you're looking at a binary star is the brightness of the star, which you might not be able to resolve the two stars separately in a telescope. So instead what you'll see is the star start bright, it will get dim as one of the stars goes in front of the other, and you can no longer get the light from the back star. And then the two stars separate, and they are equally bright. And then the second star blocks out the light of the first star, and it dims again. And then it dims again. The distance from here to here, that's when star 2 is in front of star 1, and here star 2 is once again in front of star 1. So this right here would be the period for each of the stars, because this means star 2 has gone around and is back where it started or has completed one cycle. So in this case, we'll take the two stars have a period of 2.6 years, and we'll say that we know that the distance between the two stars is 8 astronomical units. An astronomical unit is the average radius of the Earth's orbit around the Sun. Then we can ask, how massive do these two stars have to be if they're that far apart and they have this period? Now, the way we set that up is, again, we're just going to use F equals ma. The force is the force of gravity, because the only force acting on this star would be the force of gravity from the other star. Distance between them is the diameter of their orbit. So that's gm squared, because the two masses are equal, divided by d squared, the distance between them. That equals mv squared over r. And here the radius of the orbit is half the diameter. The period is 2.6 years. We convert that to seconds. The diameter is 8 astronomical units. We convert that to meters. The velocity is pi times the diameter divided by the period. So this is the velocity. And once we know that, we can plug it into this formula and find out the masses of each of the stars. They're extremely massive. It's about 38 times the mass of the Sun.